So in today's class, I will discuss the basic concept of stress and strain, and I would like to generalize this basic concept stress and strain. So as we are from the different disciplines, some of you may be from the mechanical, some of you may be from the civil, some of maybe you from the aerospace engineering. So as we go higher, so we can observe the gap between the multidiscipline will be reduces. So the outcome of any industry product is the handshaking of the different multiple discipline. So for example, just like the nature is the best example of engineering, and we all try to understand the nature, we all try to mimic the nature, and this nature is governed by the certain rules, and we all try to understand these rules, and understanding of these rules is not just enough. We have to understand and also has the capability to translate these rules so that we are able to serve the mankind, so that we are able to develop some product which is very helpful for the mankind. So when I was selecting this PPT, so I will try to cover all the engineering discipline so that we are able to understand. These all are the example of the multidiscipline engineering products, right? Just like we can start from the bridges, and we can see the nano robots, and we can see the man-made different automobiles, switches, human system, different kind of machineries, motherboards, and jackets, and optical fiber, CD, and capsule, and we can also see the SIM. So these are the some basic example which is the multidiscipline criteria examples. So these products are designed for the different purposes. To design these products, the different skilled are required, and the main important thing is, and these different products are served in the different reason, different purpose, and the main important parameter we can observe here, these all products are made of the different materials, right? Just like the material used for the bridges is not same as the material used for the nano robots, and the material used for the nano robots is not same as the material used for the switches. Same way, the material used for the motherboard of any computer is not same as the material used to make any bulletproof jacket. Same way, the material has the different purpose, material has the different environment in which it has to be served, is used. So these are the different kind of product used for the different purpose. So the important parameter is here, these all are made of the different material. So if all are made of the different material, then we have to select the proper material for the particular purpose, right? So what happen in the case of material, if we are selecting any material, so we have to keep in mind which kind of threat a material is subjected, so that according to that it will give the response. This threat word is very important here. Threat is very subjective word. The very subjective word means threat is not only restricted to the how the different kind of load acting over the material, and in which environment the material has to be used or be served for the different purpose, and according to that threat and how this is responding basically about these different kind of threats. So these threat may be the load acting over the material, and due to that threats how the material is responding in the different environment, and this threat could be the different environment. Just like for example, if we are designing a aircraft, generally the environment for the aircraft is nearly about -40 degree to -50 degree centigrade. So we have to select a material which are able to serve the purpose in -40 to -50 degree centigrade temperature, and the material used for the bridges is not have such environment, it is just has to sustain only 25 to 40 degree centigrade. So the material used for both the purpose has to be served the different purpose basically, right? One is we have to design in such a way, we have to select a material that can sustain temperature -50 degree, And in bridges, we have to design in such a way, and we have to choose a material that can sustain up to the 40 to 50 degree centigrade temperature. So the threat is very important parameter here. How the material is threat. How the material is threat means how the different kind of load acting over the material, and how in which environment that material has to be served the purpose. And according to that, the material will respond. And this response is very important term. So how the material will respond against the threats, that I will discuss in the later. So basically, when I am talking about the threat, so it is the any kind of load acting over the material and the environment in which the material has to be used. And the response has three important parameter. One is stress, another is strain, and the relation between stress and strain. So these are the response of any material when any material is subjected to the load. So how the stress induced in the material, how the strain induced in the material, and what is the relation between them. And this relation, stress is a function of strain, and this is called the material constitution. Material constitution means it is characterized how the stress, strain, and the relation develop in the material. So before going to the proper definition of stress, I would like to correlate this. Stress is a very general term in every context. If I am saying a person is stressed, right, just like a material, so this stress is not only the restricted to the elasticity only. Materials, it is not restricted to the materials. It is a very general term. It can be explained in every context. Just like any person is stressed. If I am taking an example, I am saying a person is under stress, right? So a person may be under the stress. There are so many regions of that stress. There may be a problem of relationship. There may be a problem of workload. There may be a problem of family. There may be a problem of study. There may be a problem of future. And there may be a problem of billings. There may be career. There may be a lifestyle. So these are the different kind of threat a person can sustain, a person can bear due to that he is under stress, right? So a person can be under threat, and how these threat acting over the body of human, and how the human body is responding against these threats. The main important thing is that the stress is how the body is responding against the threat. So human body, how the responding it is against the threats. It is very important, this stress and strain concept. So that's why I'm saying stress and strain only not restricted to the material of elasticity. It is a very common and general terms, and we can correlate with general to the material of elasticity. In later class, I will discuss how we can correlate these very general terms with the material of elasticity. So threat may be anything to the human being. If I am saying I am stressed, so it may be due to the any region. If I am due to any region I am stressed, so my body will respond. And what is that respond? There may be a possibility the blood pressure will increase. There may be the possibility the weight problem will increase. There may be a possibility the hypertension increase, just like this. So if a person is under threat, what happen? There may be a reason of hypertension, there may be a reason of heart disease, there may be a reason of skin problem, there may be a reason of weight problem, there may be a reason of pain. So these are the consequences of the threat. If any human body is subjected to the threat, so what are the consequences? The body will feel stress, but stress cannot be visualized, it can be experienced. Only the visualized thing is the consequences of that stress, that is called response. Another response that is called strain, that can be visualized and measured. So these are the consequences of the threat: hypertension, heart disease, skin problem and weight problem. And these consequences can be observed by anyone and these can be measured. But a person feeling the stress cannot be measured. It can be experienced by the person only. no one can visualize, no one can measure, only the sufferer can experience the stress. No one can see the stress. Only the consequences of that threat can be seen by or visualized by or measured by the other person. These consequences are like this. So I can simply say, with regarding to if I try to explain in the context of material, if any material is subjected to any kind of threat, and this threat may be any kind of load, this threat can be any kind of load or environment in which the material has to be used, the material will respond. And what are the responses of the material? One response of the material is called stress, another response of the material is called as strain. So how the body will respond against the threat? If human body, just like in previous example we have seen, if there is any threat on the human body, how the human body behave basically, how the human body will respond. So there are two responses of the human bodies also. One is stress, another is strain. The only thing we have to understand that stress can be experienced. Just like a material, if I am taking any example, if I have any material, just like if I am having a cup, if I apply a force on the cup, if I apply a force on the cup, so, and suppose the cup is made of any material, that is plastic material, if I apply the force, there is a possibility some deformation will take place. So we can easily understand that cup experience, after the application of the force, that cup experience the stress, but no one can visualize that stress. Only the material can sustain that stress. Visualization is the deformation. So visualization part is the strain. I am repeating the same example. If I am considering a cup that is made of plastic, if I applied the force, right, or you can say thermocol. If I am taking a cup, just like a cup of tea, if I am taking a cup that is made of thermocol, if I applied the force, so definitely it will crust, and it will crust. Only the other person can see visualize or measure the strain. The stress cannot be measured by or visualized by the another person, right? Only the strain can be measured, because we are able to visualize the strain, because the deformation we are able to observe, right? So that's why any material has two response under any kind of threat, that is stress and strain. Stress can be experienced by the material, it cannot be visualized by the other person, but strain can be visualized or measure. So that's why it is very important to understand the response of a material, and we can correlate with the human body also. If any human body is under stress, so stress can be experienced by the person, but the consequences of that stress on the body, just like the hypertension, pain, weight gain, can be visualized by the other person. So that's why stress can be experienced and strain can be visualized, right? So we have to understand this. We have to. So before moving to the proper definition of stress, go back to your school days. In school days, what happened? We have listened this word very common. What is stress? What is strain? And we have simply seen what is stress. If I am considering any bar and it is subjected any load, suppose this is a bar and subjected to any load and any cross section area. Suppose the cross section, if I am considering this is the cross section area A. So what is the stress here? Simply define the stress is nothing else, it is the load by area, right? So simply stress says the load by area, and A tends to 0, nothing else. In our back days, in our school days, we have seen this definition so many times. The stress is nothing else, it is the load by area. So now we have to move beyond this definition actually, because this definition There is no problem with this definition. This is also the proper definition, correct explanation, but there is a need to go beyond this definition now. Actually, because this definition, if I am defining, if I am asking stress is force per unit area, so which force, which area I have to consider after the application of the force. Suppose there is a change in the, suppose the initial length is L, after the application of the force, the change in length become delta L. So I can also define what is a strain. So strain is nothing else, that is the change in length to the original length. So there is nothing wrong with these definitions. These are the absolutely fine definition and correct explanation. But now we have to move beyond this definition, because these if I am asking what is stress, is load by area. So the question come into the mind, which area, which force, which direction length I have to consider after the application of the force. So many things come into the mind. So that's why for engineering student it is mandatory to move beyond this definition, because this is not the correct. I am not saying it is absolutely fine definition. There is no problem. Every time I will restrict to this definition, load by area, load by area. But we have to understand which load, which area, which dimension we have to consider for the different part of stresses, right? To understand that concept, I am considering an example. In this example, there are some books kept over a inclined plane. Suppose the inclination of this plane is theta, and the weight of the book is W. This W will act in the downward direction, and definitely everyone know that the weight has two components. Suppose this component is W1 and this component is W2, right? If I am considering this plane area, so this plane area has two components of the force. One we are saying W1, another one we are saying this is W1 and this is W2, right? If I am writing here what is stress, so simply I can write stress 1. I am not giving any notification now, any how to denote the stress. In the consequent classes I will discuss all the things. So I am keeping very simple. So I am just writing what is stress 1. I am saying here stress 1 is, suppose this W1, and suppose the area of this plane is A, W1 by A, and I am saying stress 2 is also there, and this stress 2 is nothing else, that is the W2 by A, right? So now this stress has two components, right? One is W1 by A, another is W2 by A. So the load acting W2 is called normal load. So the stress produced is the normal stress, because it is the normal load, normal to the surface. So if the load is normal, the stress produced will be the normal stress. Another load is the tangential load, that is the parallel to the surface. It is perpendicular to the surface, and W1 is the parallel to the surface. If the load is parallel to the surface, the stress produced is shear stress. So now we can simply see that the component of this stress, one is normal component, another one is the shear component. So it is very important to understand. I am only restricted to the definition. What is stress? Load by area. What is stress? Load by area. Which load I have to consider? One is the normal load. If there is a load is normal, the stress produced is the normal stress. If the load is shear, means tangential, the stress produced is the shear stress, right? So we can easily simplify, easily see the component of the stress. Now we have two component of the stress. One is normal component, another one is the shear component, right? For the similar example, now it is also very important. If I am saying that this is for three-dimensional. If I am considering this is three-dimensional body, just like you can see, you just mention it. If I am considering the three coordinate system here, one is X, Y, Z. If any force is acting, suppose the P force is acting in an inclination, this P is making angle with all three axes. Then there are three components of this force. And what are these three components? And these three components of the force will be just like you can say it is one component along this line, one is normal to this, and another one is like this. So suppose this is W1, this is W2, and this is W3. If I am considering a 3D concept, so in 3D concept we can understand I am considering a coordinate axis X, Y, and Z, and this is subjected to a force P at an inclination, and the inclination of the P from every axis. So these P has the 3 component in the 3 different direction. One direction is W1, other is W2 and W3. Again I am restricting to the same definition. Stress is nothing else, load by area. So how can I write? Stress 1 is equal to W1 by A. Suppose the area of this plane is A, and stress 2 is nothing else, that is also W2 by A, and stress 3, and we can observe W3 by A. Now, so this W1 is normal load, so which stress it will produce? Normal stress. So this stress will be the normal stress. And other 2 component are, this component is tangential to the surface, another this W due to the W3, again this is tangential to the surface. So this component will produce shear stress, and this component is also tangential to the surface, so this will also produce the shear stress. It means in case of 3-dimensional body there is a 1 normal stress and 2 shear component. Now we can see we are only restricted to the same definition. Stress is nothing else, that is the load by area, but we have to understand that these stress has a different component, and that depend upon the plane, because we are having the same area, and the same area the stress is different. One is normal, 2 are shear. So these are the shear stresses, and this is the normal one. So now we have seen stress has some component, and these components are very important to explain the stress implicitly, right? So after that the question come into the mind when we are studying the stress. If I am asking a question, what is the value of stress in a body? What is the value of stress in a material, in a point, or in a material, in an object? So actually this question is not posed properly, because stress and strains are the point phenomena, point description. Stress and strain are the point description. It is not the area and volume description, right? It is not the plane description. So stress is always implicitly, if anyone is asking what is the stress in the body, so mainly he is implicitly asking stress at a point in the body, because suppose if I am considering, that's why the concept of infinitely small area and volume is very popular, right? If I am considering there are different points on the body, now I simply say every point subjected to the different stress, because stress and strain are the point description. So if stress and strain are the point description, so it has different stress and strain at the different point, right? So every point is having the different stress and strain. So but we have decided stress is load by area, but we are restricting to the point. So how the stress can we explain at a point, because point does not has any dimension. If point does not has any dimension, so how we can say it is load by area, right? So just we are taking an example, that's why we are taking very infinitely small dimension. Suppose this is the point, I am idealizing this point is an area, very infinitely small area. This is, suppose if I am making here it, so this point is nothing else, this is, suppose this is dx, this is dy, and how I can consider dA is equal to dx into dy, right? So I am idealizing this point as a area, infinitely small area, right? This area tends to 0. If this area tends to 0, this become infinitely small, this become point. So it is, this figure is representing, if I draw the larger view of this, suppose it is the 2-dimensional body. So how the stress acting over this body, if it is 2 dimension, this is suppose one stress is acting. These are the normal stress, right? Another stress is the, you can say, the shear stress, right? So these are the description. These are the, suppose this one is due to the W1 and this is W2 and this is W3, right? So W1 and W2 are representing the normal loads, so they will produce the normal stresses. So here we can calculate again, stress 1 is equal to W1 by A, right? And this area is very small, dA, and stress 2 is W2 by dA, and stress 3 is W3 by dA, right? So in this way we can define stress at point. This figure is representing stress at a point. Right? So stress is a point description. Stress can be defined at a point. If I am, because the point does not have any dimension, so if I have to consider, that's why I am considering infinitely small area and volume, right? So that I can consider infinitely small area and volume. If it is restricted to the 0, this area is 0, that become a point. If it is a 3-dimensional point, if I am considering the same point in the 3 dimension, just like this body has the different point. If I am considering any 3-dimension point, if I am idealizing any point like this, if I am making this view here, because stress is a description of point, stress always a description of point. So how can I idealize this point? So this point now we can see subjected to the every plane. Suppose this is x-axis, this is y-axis, and this is z-axis. So these are the, this way we can explain every plane is subjected to the 3 component of the stress. One is normal, another 2 are shear component. Similar way I can explain over it like this and like this. This is the normal component and these are the shear component. Same way on another plane I can explain. So that's why the concept of infinitely small area and volume is very popular. In 2D it is area, in 3D it is volume. So that's why the stress is a point description. So stress can be explained at a point always, not on the body, entire body. So whenever anyone is asking what is the stress in the body, so implicitly he want to know the stress at a point, right? So so what is the definition of stress? Generally I am restricting, I am not going beyond that because this content belongs to the first year student. So what is stress actually? So stress is generally defined as the internal resistance force per unit cross section area, right? So how the stress can be defined? Load by area. If we cut any material from any cross section, so we will observe some resistance offered by the material. So generally the stress, it is represented by sigma, right? So what is sigma? What is stress? Stress is nothing else, that is the internal resistance force, per unit cross section area, right? Internal resistance force, if we see, suppose we are considering a bar, it is subjected to force P. If I cut it, so I can easily observe the internal resistance offered by the material against the load. So that internal resistance per unit cross section area on which area it is acting is called as the stress. Stress is represented by sigma, right? And generally numerically we can say, numerically we always write this internal resistance force is equal to external force, and what is the external force we are considering here, and this external force is nothing else, that is the P, and this is A, and what is this area? This area is the cross section area, and this stress is basically the normal stress, because the load acting normal to the surface. If the load acting normal to the surface, that will produce the normal stress, right? So we have already discussed how the load is acting here on this area. This is the normal to the surface. If the load is normal to the surface, the stress will produce the normal stress. So simply we can define what is stress. It is the internal resistance force per unit cross section area, right? And beyond this, we can see the unit. The unit is Newton, the force unit is Newton, and area is meter square. So the unit become Newton per meter square, and this is also called the Pascal. And Pascal is very small unit, that generally the stress is represented in kilo, mega and gigapascal, and these are the notation for that, and we can also convert into the Newton per meter square, right? So it is very simple concept. Stress is nothing else, it is the internal resistance force per unit cross section area. And which kind of stress, either it is compressive or tensile, that coined based on the external load acting over the body. If the load acting tensile, the stress will produce the tensile stress. If the load acting is compressive, the stress produced will be the compressive stress. Just like this, if I am considering any body, any object, if the load acting, which kind of load is this? This is the tensile load. So in that case, the stress induced will be the, here the stress induced will be the tensile stress, that will be the load by area, right? Generally internal resistance force per unit cross section area, but numerically to solve the numeric, because we have to solve the problem, so we always consider internal resistance force is equal to the externally applied force. If the load acting over the body is compressive, means like this. If the load acting on the body is compressive, so in that case the stress induced is called the compressive stress, and it is taken by the negative sign, because in that case there is a elongation. After the application of the force, the body will elongate, the length will increase and diameter will increase. But if the load is compressive, in that case the length will reduce and diameter will increase. So that's why the negative sign come into the picture in case of compressive stress. So whenever you are representing the compressive stress, you can represent it with negative sign. Whenever you are representing the tensile stress, and both are the normal stress, right? After that, we have seen the types of stresses, how we can define the types of stresses, the normal stresses and shear stresses, right? As already I have discussed normal and shear, right? So normal stress, we have seen that internal resistance force per unit cross section area if the load is acting normal to the surface, right? Shear stress, if the load is acting tangential to the surface. If the load acting tangential to the surface, means if I am considering any body, suppose this body is fixed at the bottom and it is subjected to the tangential force like this. So how there is a possibility of deformation. Suppose this angle is phi, the change is phi, angular deformation, because one end is fixed. If you are applying the tangential force, so there is a possibility of shape change. So in that case also the shear stress is nothing else, it is the load by area. Here the area is considered as the surface area. Here the area is considered as the normal area. Means perpendicular to external load. Here area we have to consider, that is the parallel to external load. Okay. Further, the explanation of these stresses I will discuss in the next classes, how these are classified into the different ways, normal and shear. Thank you.